All right, in this video, we're going to introduce conservative vector fields. And so we say that a vector field f is conservative on a region D if there exists a function phi such that f is equal to the gradient of phi. And we call phi here a potential function for the vector field f. Okay, so in the last section, we talked about gradient fields. So if I start with a function phi and take its gradient, that will give us a vector field. So if we turn that around and say, okay, now I have some given vector field f, how can I determine whether or not there is a potential function phi whose gradient is equal to f? Well, that's one of the main questions we're going to address in this section. Okay, and fortunately for two-dimensional vector fields, that's relatively easy to check. Okay, so this following test to determine whether or not a two-dimensional vector field is conservative or not is as follows. So if f is pi plus qj, and this thing is defined on the open set D that's both connected and simply connected, and p and q have continuous partial derivatives on D, then f is conservative if and only if the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. Okay, so you can see some of that terminology from the last two videos already making an appearance. Now this condition on D being simply connected is crucial, okay, for the if and only if statement to hold. And we'll look at what can happen when D is not simply connected a little bit later. Okay, but for now, let's go ahead and prove one of the directions here. So if we assume that f is conservative, why does this derivative condition have to hold? Okay, so if f is conservative, well, then it's the gradient of some function phi. And so if I equate components here of these two fields, right, the I component of f is p, and the I component of the gradient of phi is partial phi partial x, so p is equal to partial phi partial x then. And likewise for the j components, we would have that q is partial phi partial y. And see now if I differentiate p with respect to y, that's the y derivative of the x derivative of phi. And this is going to give us this second order mixed partial derivative. And then likewise, the x derivative of q is the x derivative of the y derivative of phi, which is this other second order mixed partial of phi, and we know under certain nice conditions, which are being satisfied here, Clairaut's theorem says that these two mixed second order partial derivatives are equal. Okay, so in other words, partial p partial y must equal partial q partial x if our vector field is conservative. Okay, now going the other direction, so if we know this derivative condition holds, how do we then prove that f is conservative? Well, I'm not going to prove that in this video, but there is at least a sketch of the proof in the text if you'd like to check that out. Okay, so now let's go ahead and highlight this warning because this is going to be something that will come up um, quite a bit in a few things to that will follow later on. So I say here that the condition that D is simply connected is necessary. So in other words, if we know that partial p partial y is equal to partial q partial x, but D is not simply connected, then f it may or may not be conservative. There's no guarantee. You're going to have to do more work in this case. Okay, so we're going to see some problems in the worksheets this week that address this issue, and also problem number 2 in this week's quiz deals with this as well. So in quiz week 7, okay, it deals with this particular issue where you're working over a domain that's not simply connected, but this derivative condition still holds. Can you say whether or not the given vector field is conservative or not. Well, in some instances, yes. In some instances, no. Again, you have to do more work. All right. Well, let's now go to problem 2. Okay, so this says determine whether or not the vector field's conservative. If the vector field is conservative, find the function phi such that f is equal to the gradient of phi. All right, so starting with A here, we have for p, the I component, which is 3 plus 2xy, and q, this is x squared minus 3y squared. So if I differentiate p with respect to y, I'm going to get 2x. And if I differentiate q with respect to x, I also get 2x. And since the domain here of this vector field is all of R2, right? Certainly simply connected, right? So, I mean, no holes, nothing along those lines to worry about. This implies that f is conservative. All right, so now our job is to actually go about finding a function phi whose gradient is equal to this field f. Okay, so now here's what we're going to do. If we're conservative, then we know that this p function is equal to the partial derivative of some function phi with respect to x, and we know that q is equal to the partial derivative of phi with respect to y. Okay, so if I take this condition to start, that partial phi partial x is equal to p, which is 3 plus 2xy. Let's go ahead and integrate with respect to x. So that's going to tell me that phi is a function of xy. Integrating with respect to x will give us 3x plus x squared y plus some constant. But be a little careful here, right? When I integrate with respect to x, I'm holding y as constant. So I'm going to write this as c of y. So this right here is a function that depends, it's not a true constant. It's constant with respect to x is really what we're saying here. So it depends only on y. So how can I go about then finding c of y? Well, what I could do is differentiate now with respect to y. So I'd get that partial phi partial y. This is going to equal, has a derivative of 0 with respect to y. This is going to give me an x squared, and this is going to give me c prime of y. But see, I know that partial phi partial y is equal to q, and so now I can equate this with q, which is x squared minus 3y squared. All right, so this right here is just q. And I can see from this equality, right, that I have this x squared here and this x squared here. So that implies that it must be the case that c prime of y is equal to minus 3y squared. So if c prime of y is minus 3y squared, then c of y, being the antiderivative here, would be minus y cubed plus some constant. And I don't want to use c because I already use c up there, so I'll just say a for some constant. All right, so now putting that all together, we can say this. Our potential function phi is equal to, well, 3x plus x squared y plus c of y, which we just found was minus y cubed plus some constant. Okay. So you can easily check that this works, right? If I take the gradient of this, well, the I component would be the x derivative. And what's the x derivative? It'd be 3 plus 2xy, and then this has a zero derivative with respect to x. So 3 plus 2xy. Yeah, that works. How about the y derivative of phi for the j component? Well, the y derivative is going to be x squared minus 3y squared, and that's exactly what I have for q. So it works. Cool. All right, and then how about part B? We have f is minus yi plus xj. So here is our p, and here is our q. So if I differentiate p with respect to y, I'm going to get -1. And if I differentiate q with respect to x, I get 1. And notice these are not equal, and so that implies that f here is not conservative. Okay, so again, our domain is nice, right? This thing is defined over all of R2, which is simply connected. But since these things right here are not equal, then we can conclude that the field is not conservative. Notice that this is the rotation field that we introduced back in section 15.1. We're going to be doing a lot with this rotation field and some variants of it in the next couple sections. All right, well, that'll do it for this video. Thanks.